Operating procedures, often called SOPs, are intended to provide site-specific instructions for the operator's routine tasks such as starting, stopping, and monitoring equipment. The RMP and PSM regulations lay out the prescriptive requirements for SOPs. SOPs must provide clear instruction for operating the ammonia refrigeration system, address each operating phase such as startup, shutdown, normal operations, and emergency operations, incorporate equipment operating limits, consequences of deviation, and steps to correct or avoid deviation. Include safety and health considerations such as hazards of ammonia, PPE requirements, and first aid measures. Reference relevant safety systems such as ammonia detection, e-stops, and relief valves.
SOPs are a key tool for an operator, but there is an inherent challenge with SOPs. Unfortunately, the prescriptive requirements of RMP and PSM can often make an SOP look intimidating. Here's what I mean. Prescriptively, SOPs are required to address the operating limits, the consequences of deviation, and the steps required to correct or avoid deviation. And maybe even as I was saying those words, you kind of tuned me out because it sounds a bit intimidating. That's just not the way we talk. But what does that mean? Well, what's the maximum pressure? What's the minimum pressure? What's the maximum temperature? What's the minimum temperature? So the important thing for the operator is to break it down into what does it really mean and what's the intent so that the SOPs are usable, understandable, and correct.
It should go without saying, but SOPs must be accurate. RMP and PSM require that operating procedures be reviewed as often as necessary to assure that they reflect current operating practice. Additionally, if an ammonia refrigeration system has over 10,000 pounds, the SOPs must be certified annually to ensure they are current and accurate. There are many helpful resources for developing SOPs. Manufacturer literature is a great place to start. IIAR has excellent templates available in their published literature. SOPs will be unique to a specific system, but some operating procedure steps are generally universal. When starting a compressor, the operator must make sure that the lubrication system is ready. This means that the oil must be at the proper level and temperature. Reciprocating compressors are configured with a crankcase oil heater, and screw compressors have oil heaters in the oil separator. These are designed to be on when the compressor is off or in standby mode. This prevents ammonia vapor from condensing in the crankcase or oil separator and ensures the oil will flow when the unit starts. Oil heaters are typically controlled by a thermostat to shut off at approximately 100 degrees Fahrenheit. It is unnecessary for the oil heater to be on when the compressor is running because the heat of the compressor is sufficient to maintain good flow characteristics in the oil. Once the lubrication system has been verified, the operator must ensure that the condenser is running. Most ammonia refrigeration systems utilize evaporative condensers, which means the operator must verify the condenser fans are running and the water distribution system is operational. A compressor must not be started without adequate condensing capacity or high discharge pressure will ensue. Next, the operator must verify the ancillary equipment such as oil cooling system and oil pumps are ready for operation. These will vary from compressor to compressor, so the operator must have access to the original equipment manufacturer or OEM instructions. Finally, the operator must confirm the compressor suction and discharge valves are open. Once these steps and other site-specific procedures are followed, the compressor can be started. Many compressors can be started in auto or local modes. Auto means the compressor will be started and stopped automatically based on algorithms in the control system. In local, the compressor will be started and stopped by the operator using the switch on the compressor panel. After starting a compressor, the operator must monitor it closely to ensure it operates safely within the operating limits of the system. Screw compressors are typically protected from short cycling by an anti-recycle timer. A motor is supplied with excessive current at startup. This is called in-rush current. Because of this, repeatedly starting and stopping a compressor is not recommended and will result in premature motor failure. The anti-recycle timer protects a motor from this by preventing the motor from starting for a predetermined duration of time after being shut down. For screw compressors, the anti-recycle set point may be between 10 and 30 minutes.
For two-stage systems, the high-stage compressors must be started before the booster compressors. Rotary vane compressors are always used in booster applications, so this step would be necessary. Rotary vane compressors are often cooled by an oil jacket since water may freeze in a low-temperature application. The oil cooling pump must be started before the compressor. Another nuance for rotary vane compressors is that they are typically started with the suction isolation valve closed. Once the compressor is operating at full speed, the operator will slowly open the valve and monitor the suction pressure. Once the suction pressure stabilizes, the valve can be fully opened. When starting a compressor, the operator must make sure that no liquid is allowed to enter the compression chamber. If loud noises are heard at startup, it may be due to liquid slugging. Immediately shut off any compressor suspected of liquid slugging. Slugging can be caused by a high liquid level in the supplying vessel, such as a suction accumulator. Slugging can also be caused by a rapid drop in suction pressure, resulting in liquid carryover. Regardless of the cause, slugging will have devastating mechanical effects on a compressor, especially a reciprocating compressor. Because liquid is incompressible, liquid that enters a cylinder can cause permanent damage to valves, pistons, and connecting rods. In screw compressors, liquid can damage screws and cause the rotors to separate. Liquid in rotary vane compressors may break the sliding vanes. When a compressor is in auto mode, it will shut off automatically based on the system's suction pressure. Operators can shut off a specific compressor at the PLC HMI or directly from the compressor control panel. In an emergency, an e-stop on the compressor panel can be activated. Alternatively, the system e-stop, which is typically located outside the machinery room, can be used to shut down all compressors at once. The condenser must be running before any compressor is started. To start an evaporative condenser, the operator must first make sure that the water level in the sump is adequate and the mechanical float is functioning. Condenser water chemistry must be maintained to prevent scale buildup and growth of algae or harmful bacteria. The operator should ensure that the chemical treatment system is functional. Next, the operator must turn on the condenser pump, followed by the fans. Depending on the configuration, this might happen at the PLC HMI or a switch and light panel. Once it has been verified that the fans and pumps are running, the operator must ensure that all valves are in their proper positions. The inlet, outlet, and equalizer isolation valves must be open. If the system is equipped with an auto purger, the foul gas isolation valve will be opened as well. Once the evaporative condenser is running, it should be monitored by the operator for a period of time to ensure it is free from abnormal situations such as ammonia or water leaks. Water-cooled condensers are started similarly, except the steps related to water chemistry and fans are associated with a remote cooling tower instead of the condenser itself. Air-cooled condensers do not have water, so no water treatment, sump level, or starting of pumps is necessary. Typically, condensers are shut down at the PLC HMI. Individual fan or pump motors can be shut off at the electrical disconnect on the MCC panel. Starting an air cooling evaporator is typically performed at a PLC HMI or control panel. Turning an air cooling evaporator on means that the fans are energized and any control valves are in auto mode. All evaporators are supplied with liquid ammonia, so the liquid feed valve group will be configured with a solenoid valve. When the evaporator is on, the solenoid valve is automatically controlled. In gravity-fed or flooded systems, the solenoid valve will be interlocked with a float switch or level probe on the surge drum. In direct expansion or pumped overfeed systems, the solenoid valve may be controlled by the room temperature. Either way, the operator must ensure the valve stem is in the automatic position before starting the evaporator. Other control valves, such as motorized expansion valves and inlet pressure regulators, must also be correctly positioned prior to startup. If the defrost system is controlled separately from the evaporator control at the PLC HMI, the operator must ensure it is ready for use when required. Typically, air cooling evaporators are shut down at the PLC HMI. Individual fan motors can be shut off at the electrical disconnect on the MCC panel. Heat exchangers used to cool a fluid are started similarly to an air cooling evaporator, except instead of having fans, these units will typically have one or more pumps that need to be activated to start heat transfer. The control valves associated with heat exchangers are similar to those of air cooling evaporators. Heat exchangers are usually started and stopped from a PLC HMI or a dedicated control panel.
The steps to follow when starting an ammonia pump will be specific to the pump manufacturer, but once in normal operation, the pump will start and stop automatically based on pressure differential, or may be controlled by a variable frequency drive, or VFD. For systems with PLC control, individual pumps are typically controlled at the HMI or from a dedicated pump control panel. Open drive pumps, such as the Cornell CB series pumps, which are widely used in ammonia refrigeration systems, have additional steps such as ensuring the oil reservoir is full and functional.